So I'll be sharing a little bit about SolidWorks, like starting steps, things you need to know, and I'll also go a little bit slightly advanced just to like show you like steps I take when I'm working on a design to kind of give you an insight of what you should look towards learning. So I'm still a learner myself because every day is a possibility of growing, and I always try to learn new things every time, improve on what I know, learn from others, and constantly grow because that's what life is all about. So now, first of all, we all know what SolidWorks is. It's a 3D software we use to design stuff, simulate, and ensure that whatever we are designing is suitable for manufacturing for consumers to finally use. And SolidWorks is used in a lot of industries. We have them used in medical industries, in and robotics industries. A lot of product designers use this, mechanical engineers use this as well. And SolidWorks is quite broad. We have also the electrical part, and the electrical engineers also make use of it. But it's been known to be like a mechanical software mainly because I guess that's it's used mainly by mechanical engineers in the field. And uh, the reason why SolidWorks really matters in the mechanical field and whatever you're using it for is because you can easily bring your idea to prototype and then to manufacturing. And the software is really, there are a lot of softwares out there, but for me, I've always seen SolidWorks to be like the best because I've tried some software, but SolidWorks has always been like easy to navigate, have a lot of like useful features that you could easily get to use and understand. And that's one important thing you should know about SolidWorks. It's easy for you to understand it. It's easy for you to use it. So, and I think major things you should understand when trying to use SolidWorks. Number one is your sketching. You have to understand how to use the sketching tools. I don't know, I'm sure a lot of you have played around with it. You done your extruding, done a lot of like revolve and stuff. And that's like the basic thing you do when using SolidWorks. But the problem is, how do you combine all these features? How do you think about a design? How do you go about making whatever it's in your head actually show up in your CAD model as what you need, not just putting something there, but exactly what you need the way you want it. And there's not really like a rush process to it, there's no shortcut to it. It's all about practicing. You have to practice using SolidWorks over and over and over again to like really know, okay, these features I can use them for this, I can use this for this. And you can never know everything, so it's impossible to know everything and the way to use a particular feature in every way. And what I do advise for that is to always experiment. You always experiment using different features to find a way to figure out stuff. There have been situations whereby I had to like sit down and then try different stuff just to get one thing done and stay for hours. But what you find out is after you're done with that, you get to understand what the feature is. There are a lot of stuffs in uh, SolidWorks, a lot of like parametric designing. You have parts, you have assemblies, and you have drawings, and that's like the process to getting what you need done before you start maybe manufacturing and production and stuff. And you also have your simulations to help you out with verifying the structural strengths and whatever you need to know. So let me share my screen. Uh, mm, Give me a minute, please. Okay, can you guys see my screen?
Yes, the screen is visible and clear.
Okay, so I want to use a design I did to kind of like walk you through the process of designing with SolidWorks, some of the features you should know about, and also what you should think about before moving into SolidWorks. One important skill you should have as an engineer is the ability to sketch out ideas. So you should try improving your sketching skills. It doesn't have to be great, but it has to be something you can easily understand and you can like create ideas through it. It's way easier to do that than just jumping into SolidWorks and creating different things over time, which would take a lot of time. And this is something a lot of industrial design engineers do. They sketch out ideas, different concepts. They can like check out different variations of concepts at the same time before they like dedicate their time towards creating the CAD model. So that way you don't spend too much time. Another thing is okay, I won't actually talk about that because that's going to be going too advanced. And when I talk about sketching, uh, this is part of what I'm talking about. This is not too much of a sketch, but it gives you a general idea of things you're trying to like consider. And here I'm looking at like different shapes and forms for a particular for this design, which is a monitor light bar. I don't know if any of you have seen a light bar before for monitors. It's a light you kind of like hang on your monitor. It helps to reduce the reflection from your screen to your face and also helps you like see what's going on your desk so you can easily write, type, or do whatever you want to do. And so I was trying to like design something for myself. And what I did was, first of all, came up with different concept sketches of like how the it should look, and then look at those sketches and then think, okay, what should I go with? But before I got to this stage, I wasn't going to show this, but I think I need to. Before I got to the stage, I first of all looked at different monitors and light bars in the market and then think of, okay, what shape should I go with, what dimension and stuff should I go with, and that kind of like help defined how my design is supposed to go in dimension and in shape as well. So another thing you look at is components. What components are you expecting to go inside this device? And when you look at the components that you're trying to use for your device, that's kind of like gives you an idea of, okay, dimension wise, this is what you're looking at. It might be within this range, and you see if anything within that range is okay. And then before you even consider like SolidWorks and stuff. Another thing is manufacturing as well. So most people will be using 3D printer, especially for like your practice runs and stuff. So you have to consider that the limits of the 3D printer. So you design something that fits into the printer. So I think that's all about the boring stuff. And now let's get to the fun stuff, which is SolidWorks. And so this is the model that I decided to go with. As you can see, so this is the top, this is the base, these are the LEDs. There's also a transparent screen around here. Yeah, this in blue, that's a transparent, it's an acrylic sheet. And if I decide to hide this, you can see we have the screws and stuff, screws, everything. So it's designed to have everything assembled in it. So all the components, I know how they fit and stuff. And these are the electronics they're supposed to use here. And this is how everything comes together. So one important thing I would like everyone to know is that as a mechanical engineers and using CAD, you don't have to design every single thing. There's no need to like design every single thing. You have a library available to you online that a lot of people have designed, like some electronic components, some mechanical components. All you need to do is check and verify that okay, that's what you exactly need and it fits into what you want to do, and you download those models and import them into your design. For example, this is a model that I imported, I downloaded from a different site, brought it in, and then used for my situation. So you have to be able to gauge those things, and so you save yourself time and you get things that are really needed and useful for you. Um, uh, Give me a minute so I can pull up a model that we can talk about the design process for this and see how I moved from one to another. Uh, okay, so to start designing for to get what I want, this is what I followed first. This is the first model I did. So, and in this process, I'm using think top down method. I've forgotten how it's called, but it's top down. So it's basically starting with like the full enclosure design, and then from there you start breaking them down into different components. There's also bottom up process, which is designing them as single parts and then assembling them together. So there's a two process you can follow. And I've always found that the top down method is way easier because when you're designing the part in SolidWorks, you can easily see how you already know they fit together because you're designing them together. But when you design the parts separately, you have to constantly go between models and start doing measurements and stuff, doing a lot of stuff that you'll be wasting your time on and trying to make sure that all the dimensions line up, they fit well and stuff. But with uh, uh, top down, you don't have that problem. And first of all, like I said, after making the sketch, now I decided how it's supposed to look, and the idea is going with one of this shape here as you've seen from the model. So what I did was first of all did this. So this is just a simple cuboid, like an extruded rectangle, which in my case I did this, which is a rectangle and then extruded this way. So because I noticed that the shape of the stuff is just a rectangle that I really have to like transform into something else. So a simple case scenario, I just did the rectangle extruded. And now another thing to notice is that this part is symmetric. So if you put a line through the middle, it's the same on the other side. So I don't need to like model the full thing, which might take me time. I just need to model part of it and then do a mirror and I'll get what I want. So this is half the total length. This extruded bus is half the total length. And then now I do a cut. So you have a sketch this way, and then I cut that to like get that shape that I had in my sketch. First of all, so I did the cut, and then the next thing I did, I added some fillets around this and this. So sometimes the use of fillets and chamfer, it's a little bit a lot of people have like different ideas about where to use it and so on. A lot of people, they like to use it at the end of your modeling, and some cases it's you get to do that, but in some cases you can't. You just have to put it wherever you need it. So you just have to think about that and see in your own situation what applies there. And now I have this chamfer here, trying to make it look more like the product. You have the chamfer down here, and then a chamfer up here, and the last fillet, which is this. So now the next thing is to mirror it, and then you have everything complete. So the features I've used so far: extruded board, extrude cuts, chamfer, fillets, and then mirror. These are basic features that you're going to be using a lot in SolidWorks. And so I didn't really go through all this bars and stuff because I'm guessing that's what a lot of us have already seen, and that's not something I'm supposed to do here because you can find it on YouTube and stuff. So that's why I'm mostly talking about how you use most of these features and to get a product. So now I know I've gotten this, but this is just all solid. So it's just solid. I have the outer shape, but I can do anything with it. I can put components in it, can do anything because it's just solid. Now to get uh, what I need inside, and to ensure that I'm having like a uniform thickness along the walls, because you need your wall thickness when you make it hollow. What I do is I use a feature called shell. I don't know how many people have used it. So what shell basically does, it's it's try to make the component hollow while maintaining a particular thickness all around the surface. And if you open the shell uh, feature, it's pretty simple. It's just the thickness you want here, and then you can take if it's outward shelling, or it automatically it's inward shelling, which means it shells this inside and the thickness it's inside. But if you do outward shelling, it shells the inside but the thickness goes outside, so it adds an extra layer of thickness towards the outer part instead of still using what's here, which means the original dimension you initially have here increases a little bit by your thickness. And if so, you have to understand the use space and basically what you want to use it for. If you want the thickness to be outward, so you add an extra layer, or you want to maintain the dimension you already have, then you shell it inwards, uh, which is already what you have here. So once you shell, this is what you have. And next thing I did was to cut a hole here, square hole, sorry, rectangular hole. And this is basically for where my LED is going to shine through. So that's where you're going to see the light that's inside. And then I did another cut, which is here. And this is basically for the acrylic glass to sit on. And then you can assemble other stuffs on it that way. So I have some couple of fillets around. Yeah, just beautify the whole thing. And okay, wait a minute. So another thing is, how do you want to hold this piece together? Because I still have to split the piece into two to have the top and the bottom. But now, how will I be able to hold the space together? You have to think, okay, do I want to use a snap feature, which is those components that have snaps that you push them and they snap together? Or do I want to use screws or just glue the components together or something, which is not gluing, which is not really advisable in like most consumer products. So and you have to figure out which is an easier method to use. And when you consider a manufacturer, yeah, I'm going a little bit off. Most people prefer to use screws because it's way cheaper to do than snaps. Like snap fits can be expensive depending on the design, the way you design it, it can be expensive to manufacture. So a lot of people use screws, and I went with screw here. And to use the screw you have to have somewhere they can fit in. So there are self-tapping screws, and there are screws that you need somewhere to go in. Self-tapping screws can just have a plastic, and then you thread it through, you forcefully thread it and it goes through the plastic. But I want to use the normal screw, and to use that I need to use something called a threaded insert, and put them in the place where the thread is supposed to go, and then I can have the screw put in there. And to do that, I have to create places for this threaded insert, which is this. So the extruded boss is just from this surface, from the base surface to the top surface. And then I do a linear pattern to have it here and create a plane, a mid plane. And to do this, you can use your plane and then click the reference. Maybe this is the first one, and then you click the second one, and that way you create your mid plane. But what I like to do is I use a different, like a simpler way of doing this. What I do is I just click this surface. And mind you, you have to hold control while doing this. So I click the surface, hold control, click the surface. And once I'm done, I've selected those two surfaces. I can just go here and click on plane. It automatically does that for me. And so that's like a fast way of doing that. And then I can click OK and it creates the plane for me. And once it does that, I did a mirror the uh, what we call this are buses, and that's what you call the extrusion that the threaded screws are supposed to go in. There's also a SolidWorks feature for that as well. Uh, so yeah, so there are buses, mountain buses you can, and they have different. styles for it, which I'm going to talk about in a little bit. I think I use that feature later on, but let's just go with this first. And okay, so it's now kind of like time to split. And now, so since I already have the extruded body, the extruded bust, I can now like split this into two to have the top and the base. And for that, you use a split feature. But first of all, I created a plane right where I want it to split. So I'll be using the plane as a split. Now the split feature, if you search on your command, you have a lot of splits here. You have the split line and then the split. So a split line is basically just going to cut through the surface of the part. It's not going to split it into two parts. It's just going to split the faces and stuff like that. But the split separates it, makes it two different parts, two different bodies. And that's what we're going to do here. And so if you click the split feature, what you have to do is, okay, click the plane, the trimming tool, and then you click the target if you have a selected body. In my case, it's all, and then you click on cut bodies. It's then going to bring up all this for you. So these are all the bodies that are currently available there based on what is split. And then you can click OK. If you do want to save them as individual components, you can click each of them here, check them, and then click OK. It's going to like save them as bodies. But in my case, I don't want to do that now. I want to control what I save and what I leave because I don't want to save all this. I just need two pieces out of this, the top and the base. So I close it, and this also allows you to like get the chance to do more editing inside here and then save it at the end. So you don't, so whenever you want to make a change, all you need to do is come back to this, make the change, and it will automatically update in the body you've saved. So if I move down, wait, this is another split I did, but this is particularly for the buses inside. So when I was designing this, for some reason, I left the buses as components on their own, like bodies on their own, so they're different from like the total stuff. And I think I didn't want to like mess things up, so I left it that way and just flowed with it. So another thing you also consider is grooves. I don't know if I should be talking about groove at this point since it's like a beginner's intro lesson, but let's just skip groove for now. It's kind of like an advanced feature. So what I do now is, since I have this part separate and I have the top separate as well, now I have these bosses here. So they are individual component. Now, what I want to do is make sure that, okay, one of them is to the top and the other one is to the base. So what I do is I do a combine, use a combine feature. Now, if I go into the combine feature, what I'm doing is, okay, pick the components I want to add together. So in this case, I picked the top. Pick the top component, and then I picked all the extruded bars that are connected, that touch the top part of the model, and then I say add. So I add them as one component, and then I go do a second combine, and that's basically for the base and the extruded bars that's touching. and then I do a add, and then that combines. So now if you look at this feature here, feature 3, you have just two solid bodies, which is the first combine and the second combined. So now we have the top and the base. Now the next thing to do is to actually save this as individual parts to use. So if I save it, to save it as individual parts, you just need to go to saved bodies, and then right click and then say save bodies. So it's going to save the bodies you have. You can save them and then give them a name. So, and that's how you have like your top, base, and closure. I don't know if anyone has a question so I can like answer before we move forward, or okay, if there's no question, then I'll go ahead and move to the next. So once this is saved, that's when you have the base and the top. So this is the base. Now I can do other stuff, but when you save the base, this is what it comes in as from the previous model. So it comes in as this folder from the previous model, and then you have the stock monitor live board design. So this is actually in context editing. It's actually referring to that first model that I have. And if I go to that model and make a change, it will automatically pull into this. So let's try something and see. Let's see. So in order to make a change to this model, what I need to do is I have to pull this past the save, like go back to this. So because anything past the save won't be moved to the base and the top I created. So I have to pull back and then add a feature. So let's say I want to add a circle here and then extrude it. Let's just say 50. Boom. And then do this. So I don't want to save it here. I just want to see what happens. So as you can see, it brought it in because I made the change here. So I made the change here, added it, and pulled this back to the save stuff, and then it just automatically updates here. So you can make changes in the other side, something that's going to affect both of them, or maybe one, but you want to see how it's referenced to uh, the other one, and then you save it and everything still looks okay. So that being said, if we move to the base, now I can add other features that I want for the base, and there are a lot of features you can use. So here I used a feature called slice, and it's basically just cutting through a particular plane and then getting like a sketch. So it cuts through and then gets the sketch of that cross sectional area, but this is kind of like an advanced tool, so we're not going to dwell on that. And then here I created a rib feature just to add as structural support for this. And rib features are really important. There's like a rib tool for that, and where you can use your command to search it, or you can see it in the feature tree, the rib tool, which is over here, close to your linear pattern. And these are tools that you can use to add like supports. You can also design it yourself, just use your normal extruded boss and stuff, but the reach tool makes it simple because all you have to do is just have a line that connects what you want, and then the reach tool can be used to help you do what you want. But this is slightly advanced. Like with time, over your years of practice, you get to like use them in things you want to do, and you might not really use them often. So another thing is, so now I can, because I want the ridge all around, I used a curve pattern feature, which you can find when you go to your pattern, and then you see there are different types of pattern there, which is you have the curve driven pattern feature. That way you can pattern something around a curve. And in my case, I wanted to pattern it around this curve, so I used this sketch and then pattern the stuff around. So the rest are just basic stuff. Uh, just adding fillets and drafts or trim just to make this look a little bit better. Okay, and that's all for the base. Now top on its the top model now has, that's where most of the work is done, because I'm trying to make sure my electronics attach to the top instead of the base bit, and that's why I designed this. So this kind of serves as a way of holding the components, and also a way of me attaching the stand that's supposed to connect this to the monitor. So for this, we there are a lot of features here. Uh, Let me go through them. So when you, this is what we brought in initially, and now you have to consider, okay, what else do I want to add to this to make it okay? You're a mechanical engineer, you definitely know, okay, just like the base, we have to have something structural just to make it strong, to ensure that, okay, it doesn't fail easily, is the whimsy. So, and that's why I did a rib here to kind of like do like the structural support. But now I still know that the electrical components that are supposed to go here, there are a lot of things I'm supposed to feed in. So this won't really fly. You can actually use this the way it is. You have to like cut a portion where the electronics is supposed to go, which is in our case the LED light, and then push stuff. So I can do a cut this way, so it's structurally supporting this, and it also gives room for components. And this cut is based on like the components I'm putting in. I took measurements to ensure that, okay, it fits into here, and then that's when I did this. So this place, remember, we like we said before, this is symmetric, so that's why I only did it on one part, and then created a plane and then mirrored it to the next part. So I don't have to like do for everything. Just have to do the mirror. Another thing you can also use is, instead of mirror or stuff, I could just do one of this and then use the linear pattern. So use the linear pattern to kind of like pattern it all around. That's if I did one. So like this, I could just pattern it and then put it where I want it to be. But sometimes it's not easy to like really control what happens with the linear pattern. But if you understand the linear pattern well, like you go advanced, you're going to find it easy to like control it and you can use it. Okay, I have a few questions here. Let me just see if I can go through them. So the first one is Sunday. So your modeling approach is making a master model, then you save all as individual parts and how to make them as an assembly without inserting one by one. Okay, so uh there are two, so you can save. So basically, what you said is right. I have the master model and they're separated into part. Now, but saving it into an assembly, you have to do that one at a time. You bring each of the components and then join them together. But basically, like the master model process helps, it makes you easier for you to model. You know they are going to feed into each other when you finally do. And there's also a way for you to automatically create an assembly when you're saving as. And thanks for that question. That's actually really good. So, uh, in my case, I saved them as individual components and then brought them together. But you can also have them create an assembly. So here, okay, I think I did that. Create as an assembly. So when you do a save as, there's this option down here where you see create assembly. So all you need to do is like browse to where you want the assembly created and then click OK. So it automatically creates the assembly based on how this is joined together. It automatically creates the assembly for you and then you can start doing. So it basically bring exactly the way this is here, like the two uh, components exactly the way they are here. That's how it's going to just bring it into an assembly, uh, model, and then you're going to have like the top and bottom. So basically, uh, what you're going to have is just this, the way it is in the master model. So thanks for asking that question so I could like show this. The second question is, uh, coming. Will we be able to get the part file so that we can follow your design process through the feature manager? So I haven't really published this yet because it's still a design, an ongoing design. I've not completed the design yet. I'm still trying to like finish some stuff and then probably upload it. I'm not sure yet. I don't know if it's going to be upload. I'm going to upload it or I'm going to turn it into something I sell. So it's like a personal passion project, but sometimes I kind of like sell it on like platforms for people to download and 3D print, but like on low price or something. So I think maybe you can, if you're interested in that, you can follow me on LinkedIn. I'll probably share there if I decide to like put it out so you can easily download it. But I do have some models online I could share with you to like go through some that may be less complex or something. I think I have another question from Zion. What considerations are you making for tolerances for manufacturing when this becomes a physical product? And how are you determining relocation? Is it just intuition or is it validated using calculations or FEA simulations? Okay, so two important questions. When I'm talking about when you consider manufacturing, So it depends on whether the product is supposed to be manufactured and what manufacturing method you're planning to use. So in my case, I'm planning to use a 3D printer. So whatever tolerancing I'm considering, I ought to consider how my 3D printer prints. So I've noticed that my uh, 2D printer, my 3D printer has uh, like majorly most 3D printer has like 0.5 ish. That's whatever you're putting in, there's the possibility of like having an error with like 0.5, so you have to incorporate that in your design. So if you want a hole to be 1 millimeter, I could say maybe you do like a 1.5, and then once that is done you have like the 1 millimeter. But it depends on the 3D printer you're using and the manufacturing method you're using and within what range you want. So now the 0.5 comes in when I want like clearance or stuff. That's when I'm going to use it in my case, like for the holes where this inserts are supposed to go in. So I do like the exact measurement of the insert and then add a point 0.5, which is to give slight clearance and ensure the stuff fit in. That's based on my printer. But in terms of when you're talking about tolerancing, if you're planning to manufacture it someone, you have to ask them the type of tools they have, so you know the holes that you're going to put, and then you consider, okay, between what level is it, plus or minus zero point 0.5, can I still fit in this stuff too? So if at minus zero point 0.5 it still work, at plus 5 it still work, then you say that's your tolerancing for that part. But also it also boils down to what your manufacturer has, the kind of tool they have to actually do that. So if they don't have and you give a tight tolerance, let's say zero point 0.1, it's going to cost you more. Maybe they'll have to buy new tools and stuff. Even if they have the tool, giving a little small tolerance will cost you more, like zero point 0.1. It's too tight. You're giving them no room to make any mistake. So that's what you need to consider when you're talking about your tolerance in the manufacturing method, what they have in place, and then what tolerance actually fits, and if you use your stuff will still go together. So that's for me, like I said, I'm using a 3D printer, so that's what I considered when designing this. I made sure that whatever spacing I'm putting, it's uh uh whatever space I'm putting between the components, I ensure that it's like within the zero point 0.5 range, so I know they fit in together. Like for example, this is where the top is supposed to lap to this, and you have this, so the spacing between this part and similar part on the top is around it's between, I use between zero point 0.2 and zero point 0.5, so that way I know it's supposed to fit in, because like I said, the tolerance in for the 3D printer, it's zero point 0.5, sometimes it prints okay 0.2, so I normally use between 0.2 and zero point 0.5 for my stuff. And when it comes to like determining the rib location, so the rib location, most times it's mainly about what areas are supposed to be like stressed and stuff. But for my design, if you've noticed, most of the stuffs are kind of like uniform, trying to make sure that most of them are symmetrical along the way. So, and I know this base doesn't really have a lot of like stress on it. So I just picked out particular spots in between to just add the ribs to make sure, okay, it's okay. So I didn't have to do any simulation for this. But after doing this, you could do a simulation to verify that, okay, the first I think should act on this ribs are perfectly holding it in place. It's working. You can do that. Or for me, what I do is I 3D print it, and then I try to like flex it a little bit to see how flexible it is. And the material you're using also plays a factor to this. So it might be flexible but still rigid. Not rigid, sorry, I'm using the wrong term. It might be flexible but still able to like hold the stuff you want. And that flexibility kind of helps because when it falls on the ground, rigid stuff break easily. But when something, a component is flexible, it doesn't break that much. So if it's slightly flexible and still holds what you want, it's above like the factor of safety, it has a good margin of factor of safety, then that's really good. So you don't really have to like bother much. So for this, I just did it in spots that I feel okay. This might help reduce the way it flexes, but still it still have like flexibility, and it's still able to like hold uh the component. Now for the top part, since the top will be holding a lot of components, that is why I had to like do it to go across. So it helps, it makes this part like more stronger, since it's going to hold more of the electronics. I did it across, and there's still going to be some here which I'll get to, some here that help because this is kind of where the main electronics are going to be held. So I'm hoping that answers your questions, Zion. Okay. Okay, so I'll move on. I try to wrap up real quick because I think already an hour over. So just what I was talking about right now. So this is the ribs that I added in here. And as you can see, this is a little bit longer because of the depth of this. And then I do like a cut. So still following the same pattern, and it's supposed to hold the electronics. So you see here we have like this spacing, larger spacing. And if I were to follow similar spacing here, you only have probably two or just one in here. But like I mentioned, this is where where I'm supposed to hold a lot of the electronics. That's why I decided to have three inside instead. So I have like more strength there, don't have too much bending and stuff. And aside from that, that's where like this is supposed to be held by the stand and connected to the monitor. So definitely there's going to be like a lot of force around here, and that's why uh this is more. So I think now I just added a few drafts. So these drafts are not really important in my case since I'm using a 3D printer to print this. But when I was designing this, I designed it like I was designing it for to be injection molded, to be designed with normal manufacturing method injection molding. And that's why I added this draft. So this draft basically gives it a sloped angle around here, and that's to allow for you to easily remove this component during injection molding. When the injection is done, they can easily remove the mold, and then the components can come apart easily. So that's why this the drafts exist. Uh, So I talked about mounted buses. I said these are buses, but this I did manually by myself with just an extruded bus. But mounting buses is supposed to be used for like screw or holding cases, and we have a pin bus, and then we have the normal bus that allows screws to go in. So the pin bus basically it's like a pin. So that's what you have here, and this is mostly used to kind of go through like small holes and just hold something in place. And you see the use case very soon. I'm going to show you when I go into the full assembly. Now this is how the feature is. So you basically have like a face, which is like the flat face where you want it to start. And then you have to choose between the type of bus. This is the pin bus, and this is the hole bus. So the pin bus, like I said, it's just to hold something in place. This hole bus is where you want to put your screw. And then you have other stuffs you have to set in, put in place to like give the dimension of how it's supposed to look. And then here we have fins. This one you also edit to like talk about how the fins are going to look. And the fins are this stuff. They're basically just adding structural supports to this so it doesn't easily move, it doesn't break easily. And that's why we have this. So that's the case of the mountain bus. So it's a fascinating feature in SolidWorks, and where you can find it is in insert and fastening feature. So you have the mountain bus, you have snap hook groove. This is the snap fit feature I was talking about. That's most expensive. So you can use SolidWorks to easily do that instead of like making it yourself. And I actually used SolidWorks for a very, very long time, doing most of this myself before I found out this feature. So I'm just giving you a snip look at it, but it's going to take time for you to like master how to use it because you have to go through a lot of process of like learning and doing. And what I always advise is that you should always design a lot of stuff over time. Start with simpler stuff, do realistic projects. If it's possible for you to get a 3D printer, get it and 3D print stuff. That will help you learn a lot faster than just having CAD models. So that's a way of like moving past like growing your experience, your learning experience faster. Okay, so these are other buses I did. This is the whole bus, and this is how it looks, and then the structural support. So the same similar process to this. The only difference here is we chose the whole bus and then did the dimensioning the way we want, but everything is similar process. And okay, the next thing is, so I did have like the bus stuff here. The next thing is, where do I want my screw to go in? So these holes were actually made with the uh, threaded insert in mind, like where it's supposed to go in. But for the screws are always smaller diameter than the threaded insert. And to do that, I have to kind of like cover up this hole and then create a new hole. So what I did was I created an extruded bus, cover up the holes, did an extruded cut to go all through. So this is where my screw is supposed to go in. But now you have to think about aesthetic as well. I don't want the screw to just be hanging out there. So I decide, okay, I want a particular type of screw, a countersunk screw, and I want it to be flushed with this surface. So the screw side should be on the same surface as this. I don't want it going out. And that's when you use your hole wizard and then select the countersunk flat screw, select the diameter you're trying to use. In my case, it's M 1.6 because I want it to be small, and then it creates this. So this way, when you screw in you put in your screw, it gets flush with this surface, so you don't have anything protruding out. It kind of like helps with the aesthetic as well. And then from this point on, I think created uh, an extrusion here, and then did a cut. So the cut is to allow for a charger, a USB cable to connect into this and power the system. Then the rest tends to just add in a lot of like draft angles. And all this draft I added were for manufacturing purposes. So you can manufacture it using injection molding because like I said, I was considering injection molding for this process. But the main thing I wanted to use is 3D printing, but I just wanted to improve my knowledge on like injection designing for injection molding. And think pretty much just adding fillets and stuff all around just to make it look good. So before I move to the assembly to show you how things kind of like go together, there's one thing I want to show you guys, uh, uh, the draft analysis tool here, because I'll be talking about like injection molding for quite a bit. So uh, this is what the tool does. So what I need to do is, okay, I say I want to injection mode this part, but how do I check if it's injection mode ready? I've already added a lot of like draft angles to all the surface. Now I need to choose a plane, like a mid plane, a plane where whatever mode we're using, it's going to be pulled out of the surface, and then choose a direction. So I'll choose a plane, like this is the plane where it's supposed to be pulled out of. And then now I want to choose a direction that it's supposed to be pulled out. So since this is the component I want to mold, you have two modes, one here that pulls out this way, and that one majorly will be doing a lot of like mode of this inside, and then you have another one pulling out this way. So you have two modes. So I want to see for each of those mode if it's okay. Now, based on the drafting angles I've put, I will choose like my lowest and drafting angle, which is I think in this case is zero point 0.5. I use the zero point 0.5 angle because there are some places where I use zero point 0.5, you don't need to draft them that much. And once I do that, I can now pick the direction I want to pull. So if I'm pulling this way, then this green shows you have positive, which means this is drafted enough for manufacturing, so this can easily be pulled out. But you're going to have issues with places like this. This red shows that this is not drafted or is drafted in a negative way. But if you're pulling up, you can't actually pull this. But all these parts show is okay, and this one too. Now, if I do, now you see the inside is red because you're supposed to pull down for this inside. And then you have this one being green because that hole is supposed to be created from the top, from the one pulling from the top. But this inside is supposed to be created from the one pulling down. So if I switch this to down, you see all this green to show that, okay, the down is actually going to form this and pull out, while the top is going to do this. And now you have some of this, which is just some like issues which can be navigated when you talk to a manufacturer or something. But now when you look at this complication and this complication, which means that your what's it called? Which means this mode is going to have more than just two piece pulling out, because this can't work that way. So now if I change the plane and put it here, you can see if I'm pulling from, like I'm pulling from this side, here it's all green. So I can pull from this side to pull a mode from this side to form this. So we're going to have like a top stuff, a bottom stuff, and that top stuff is going to have like maybe a hole cut out on it where we have another piece pushing in, like pins pushing in to like form this shape. And for this side, see, can form. So you're going to like, that one will need like a different face as well. Uh, Let me see if I can use this face. Okay. And then you see it's green. So you're going to have another piece kind of like similar to what happens here in here, and then pulling it out. So that those are things that you consider for like draft analysis and stuff. But this isn't actually fully optimized for like manufacturing and injection molding, because while you're able to resolve this issue out here, it's going to be harder resolving them in here. But there are ways they can do it. It's just going to be more expensive. But since my main goal is to actually 3D print this, I didn't really bother because I was okay with the way it is, and I learned a lot from doing this process. So that being said, let's go to the assembly. Mm, so this is where I pulled everything in together. We talked about the screw. These are the screws, and as you can see, they are completely flushed with the surface, as you can see. So it's completely flushed with the surface, and that's the reason I use the countersunk. And this is how the screw is. So this is how it is. And like I said, the spacing, you can see the space between here and here. It's relating to the tolerance question we have. In this case, I use it, it's a clearance stuff. So one thing is tolerancing, clearancing, and interference are stuff that their definition are very, very similar, and it could get you really confused because it also affects me a lot, because their definition are so close that it almost gets you confused. It's easy to understand clearance and interference, but tolerance is a little bit sketchy, because tolerance has to do with basically between this and this, between a positive and a negative particular value, maybe plus or minus 2 point something or something, your stuff, your design still holds. That's when tolerancing comes in place, and it's mostly for like manufacturing the product. Clearance comes in place whereby, okay, this should uh give a certain space so they can go together, and that's where you have your clearance. So you need a certain gap between these devices so they can go together. We have interference whereby you need to make sure that, okay, at this certain dimension, what dimension will you do such that these two pieces interfere with each other, that they are touching, they're going between each other. And this is mostly used in cases where you have to like use a flexible stuff and something like that. So once that flexible stuff goes in, it's like tight there and doesn't come out. There's also fit interference or something. That fit interference is whereby the stuff, the component fits perfectly. They just align perfectly into each other. But and when you're doing your fit, you also have to consider uh, your machine and tolerance. So you know that whatever dimension this stuff is, if this is a 2 millimeter diameter uh, shaft, and this is I have a hole of like 2 millimeter uh, diameter. It's on a normal like card stuff that's supposed to be a fit, but that's not going to happen in real manufacturing cases. You have the tolerancing issue to consider. So based on your machine, you know if it's going to like make less or more, and that way you are able to increase the size slightly to ensure that when the stuff goes in, it fits there and just stays in place. So that's kind of how the terminology flows around, and you get to like understanding more when you use when you work on them 3D print stuff and see how they fit together. You get to understand more about it. So this is part of like the component that's supposed to hold it to the monitor, and this is held by this screw. So it's basically tight. It's supposed to, so you can bend it and then adjust it and then hook it the way you want. And this is really tight, so you have to like force it open, or but not so tight that you need too much energy. And this piece is held to the light bulb by a magnet. So this is how it is. There's a magnet here, and there's a magnet in this piece that holds them together. So like that's the portion of the part of the portion of the design I haven't really tested out yet. So there are two magnets here. This is one, and this is the other that holds this piece together. And so if I make this uh, transparent, you can see everything going on in here. Okay, let me just hide this out and hide this. So this is our LED. Mm. And this is kind of like a support that's supposed to hold down the LED to the base. So I have different screws here. These ones go to from the base to the top to hold the base and the top together. And then this one just holds this flimsy piece just to hold the LED strip down. And then on this, we have the boss, the pin boss, and this an extruded boss here that helps to kind of like hold this here, support this here. But this is mainly held with a screw that's here. There's going to be a screw and nut holding the, sorry, a small bolt and nut holding this piece here. And you have this here as well. And this here as well. And this piece, this is connected to the top. Yeah, you can see here. So it's connected to the top, and the top holds this piece. And we also have some extruded pins here. If you take a look at this transparent stuff, that helps to hold this board so it doesn't move up, stops it from going up. And why this screw hold it in place, this one stops it from going down, so it has support everywhere. That's basically what that is, and this is what holds the electronics. So based on what I want to do, you just need these two electronics to power what I needed, and then this is the power source. Since I'm not using battery or anything, so direct power from your laptop or any monitor to use here. Mm. Okay, so I have a question here. It says, how do you write down the design requirements, technical analysis, problem definition before really jumping into CAD models? Okay, I didn't want to show this before. I was just trying to like jump into the main fun part. But so this is a PowerPoint slide I have, and normally, so this is what I do. I try to look at, okay, what do I need? And basically, most of this I write them on paper, like the drawing book I have when I'm making the sketches, because it's not really a streamlined process. Because sometimes I come up with like how the design should look first before I even talk about components, because it's kind of like both of them trying to balance each other. So the components you use kind of like define how the design should use. The design you choose to use kind of like define the components you use. So they are both like stuff you have to weigh and do like a trade-off between both of them. And so what I did was, okay, what do I want? I want a light controlled with my mobile phone. That's one thing. I want to use my mobile phone to turn it on and off, so I don't need an off switch on the device. That's what I'm trying to eliminate. Then I want it to be USB powered from my laptop. So I want my laptop or my monitor to supply the energy I need. I want it to be easily assembled, and I want it to be aesthetically pleasing. So that's like some of the requirements. And then, okay, these are the requirements. What components do I need to kind of like achieve this? So I said, okay, my mobile phone is one of the stuff I need. And then I need this controller. So luckily for me, the reason why I chose this controller is because I've used it on a previous project before and I know it worked. And I already had the component with me from the first experiment, the first project I worked on, because I bought several of it. So I still have like two left with me. So I said, okay, I could use that. Now, a DC to DC converter, you can easily get one on and stuff. And I already have one. Like I said, I used for a project before, so I already have one. Now, why am I using this LED controller and the DC to DC converter? Number one is this LED controller connects to my phone that I have an app. I can control it easily, which meets with one of the requirements. The next thing is, okay, this actually needs a specific voltage to actually work. And what I'm actually getting might not be up to or might be uh, higher than, and I just want a certain stuff. So I use this DC to DC converter to like convert whatever comes in to the particular voltage that is needed by the controller here. And if you see here, you have input 2 volts to 24 volts, output 5 volts to 8 volts. So I'm basically uh, stepping down or stepping up depending on the situation. If the voltage is more than 8 volts, then I'm stepping down. But if it's lower than 5 volts, then stepping up depending on the use situation. And in this case, I'm not really sure if I considered if I'm stepping up or stepping down. The only thing I did was I set this to ensure that whatever comes out of here is 5 volts, and that's what my controller needed. So whatever current or whatever voltage goes into it, it's just going to like release 5 volts out of it and then send. So these are the things I consider. Like that's how I go about like selecting like the requirements and stuff. I think you also mentioned something about, okay, technical analysis and the problem definition. So that's basically this, that your problem definition, that's basically part of like the requirements. You're trying to like define what you want from the product, and then you try to detect what you can use, and then uh, come up with like concepts, things that could work. As long as for the technical analysis, it's mostly comes as a result of like after designing the model, coming up with a design of what I want. Then from there, I could choose, okay, what kind of analysis can I do here? And some of the common analysis when it comes to like designing a part, especially consumer products, are like consistent analysis that you need. You have like drop analysis. That's something you want. You have the stress analysis to ensure that, okay, this can withstand whatever stress is acting on this stuff. Uh, or you have your draft analysis depending on the manufacturing method you're using. So you want to know, okay, is this manufacturable, or do I need to change some stuff, change the design? Those are things you consider. There are a lot of other technical analyses, but based on most of the stuff I worked on, these are the basic three things that I've come across a lot that you need to really, really consider. So I think can finalize on this. So yeah, I think that's basically it. Having all the components put here, and then everything is assembled. The next thing is try to 3D print and so on and so forth. Okay, our I need a few minutes. Let me pick up something. And so this is the piece. So I 3D printed the component. This is the top piece. And I don't know if you can see the kind of like bronze, kind of like yellowish stuff in there. It's insert, threaded insert that is put in there. And then for this as well, you also have the insert put in there as well for this. So this is the base. And based on what I said, so you can see it's slightly flexible, which is good. So if it falls, it kind of like bounces a little, but it's still, even with the flexibility, it's still kind of like a little rigid along the lines. So it's strong enough to hold the stuff. As you see, it's flexible and stuff. And this as well. So, which I actually do like. And this is kind of like the stuff inside that's supposed to help support the device. So these are 3D prints of this that I'm trying to like see how it goes, make changes based on what I have. Uh, I think that's basically okay. I think I can show you something off topic a little bit. So this is another project I'm also working on, and this is like a design. This is supposed to go here with it and supposed to fit in. There's also a place for a button. Okay, no, this is your USB for charging, and then you have for button. For this project, I'm almost done with it. The only thing is I'm supposed to 3D print the buttons for this, and I'm planning to use an TPU, and TPU is basically a flexible material, so it can go on here. So most of this project are stuff that I just like to work on my own, and it's kind of like fun for me. And this is part of like the component. So it's basically a design for a nameplate. And if you see, this is I think, yeah, so it's my name and then kind of like a picture of me over here. So, and then this light kind of like shine through and make you see what's there. And then I'm also planning to like incorporate an a LED around here that gives color to it as well. So that's one thing I've learned so far, that design is all about doing and seeing what you do. That helps you improve a whole lot better. But SolidWorks is the starting ground where you're supposed to start from before you're able to like get to where you need to go. And thank you guys for listening to all my rambles and what I have to say. Uh, that's it. I'm done.
Yes, Sunday, thanks for the presentation. It has been really impactful and it has been good. I hope the members they have picked the basics when it comes to designing, comes to project design, and I believe they are going to use it as a benchmark, at least to oversee and overgo whatever they have been facing. On my side, I'm so grateful that you accepted my invitation to come in despite the schedule that you have. I'm so grateful for that. And welcome any question from the members. If you have any question, feel free either to unmute yourself or to text it in the Q&A.
So I just shared my LinkedIn link to the chat for anyone who's interested in connecting with me on LinkedIn, because I use my LinkedIn as a space to kind of like share most of my designs. I also do videos to kind of like show people some of the processes I use. And if you're interested in like watching some like following up with what I'm doing, you can follow me up there. I haven't posted anything yet this year because I've been busy with work, so I haven't had time to like complete most of my personal project. But I'm planning to by beginning of like towards the middle of March, I'm planning to start focusing on the stuff again. So it'll be fine.
Okay, Sunday. So that's your certification of appreciation that I've displayed on my screen. Hope you are seeing it, and
Mhm.
I'll forward it to you soon. And for the members in, you can fill out the form I've shared in the chat, and I see how your certification and exam vouchers will be activated in your account, and communication will be done afterwards.
I think I have one question here that I need to answer. Okay. So there's a question from Treasure, and he said, "Are you going to continue with the injection molding?" So the answer is a very, very big no, because injection molding costs a lot. So injection molding part costs a lot, and for something I'm doing for fun, except if I decide to say, okay, I want to turn it into a product, and that's basically if a lot of people actually like it. But still, you can still turn a 3D and printed stuff into a product, and people buy it these days. You just have to print it properly. But injection molding, no, that's what companies do. It's not for its solo act. They are really, really expensive. They're in like the thousands of dollars, not like from like 10,000s and stuff. And it depends on like how complicated your design is. So me saying even 10,000 is like really low. So no, no, I'm not going to be doing that.
Okay, that's great. Maybe I was the one time when you are about to handle injection molding because it's one of the most tricky parts when it comes to the design part of it. After overcoming surfacing, then injection molding comes in because you have to combine so many features. You have to give in the shrinkage rate, you have to know most of the parameters when you're coming from the design field up to the end physical product. So if there is no question, I wish you the best and thanks for attending the session. Yeah, Sunday, see you soon. I think on 2027 in Nashville, that will be what the experience world. Hope you will be there.
So I'm hoping I'm hoping I will be there. I've always planned to like attend the 3D experience, but something always happens along the way, and I end up not going. But I'll do my best to attend the 2027 one.
Okay, then thanks, member, for attending the session. You can leave the session at your own time. Have a nice time.
Okay. I think I have one question, last question to answer from someone. Can 3D printing be used to make molds for injection molding of simple parts? So injection molding itself, it's something you use heat and stuff. So 3D printing would do it for like injection molded parts. But there's what we call silicon molding. So silicon molding, it's kind of like it gives you a product that looks almost injection molded like. And I've seen a lot of people experimenting with like designing the molds using 3D printed parts, and then uh, printing and then doing like a mold stuff process. So it's similar to injection molding, but with this one you don't use heat. You just use some materials, liquid materials. I've forgotten what they call them. So you use those, and once you put them, they can form the shape, solidify, and then you go through a process of like curing and doing some stuff, and then you have like a really nice product that looks almost injection molded and stuff like that. Okay, there's one more. Can we do scale down the design for 3D printing for 3D printing project if the design itself exceeds the 3D printer's dimension capacity? So scaling down is something you can do, but the problem is you've designed this and you've added components that fit into this design. So if you scale down for example, using what I have now, if I scale down that stuff to fit into a printer, the electronics won't be able to go in because it scales down everything, and you're reducing the size of the stuff, so the electronics won't fit in. But if it's something you just design that doesn't have components going into it that you just want to 3D print and use, for example, just let's say this. So this is kind of like a stand I did for like a tablet. So basically the tablet stays this way, and then like for something like this, I could I could see scaling it down a little bit to fit in could work, but you still have to test it after you 3D print it to be sure that it actually works the way you want to. So there's like there are a lot of things you have to consider when you're trying to scale down. And if you just want to use it as let's say a model you just want to keep around for like fancy or something for people to see what you did, then scaling it down is okay. It doesn't affect anything. But when it comes to like the product itself, no, you have to make sure whatever you're designing fits into what you want. So what are the most important parts step while setting up for a 3D printing? So I think what you need to, okay, after designing your stuff, you have the parts there on its own. So the next thing you do, you need to export that part out to go into the software, and the 3D printing software doesn't really affect SolidWorks part files, so you have to use it accepts step files, it accepts XTL, it accepts OBJ files. So, but I mainly use STL files because that's what a lot of people use, and that's like the uh, most acceptable way of 3D printing. So I use the STL file, send it to open the 3D printing software, and then put the model in and just adjust things. So the major thing you're really adjusting is okay, what should be the thickness of the wall that's going to be printing using the 3D printer. You select that, and then you select the infill inside because uh, 3D printers always have like this hollow inside, depending on whether you want it to be hollow and then have structures to kind of like fill in that space, kind of like saving material. So you need to think about your application step. If you really need the walls to be like strong the way you design it, then you can put like 100% infill, and that way it prints everything as complete solid the way you want. But 3D printing is something you can explore, change. You don't need too much setting. I don't really play around with 3D printing that much because I'm able to get what I want with just the simple settings. And maybe later in the future, I might decide to explore more options. And one thing you need to know about 3D printing is the way the orientation of your part also plays a role, because depending on how strong you want it, you need to put it in a orientation that allows that gives it structural strength, because the 3D printer prints in layers, which is just straight layers like this, and depending on where your force is acting on. So if you print in straight layers and you have a force acting this way, it's easier for the part to like get destroyed when it's this way because it's acting directly on the layers and they can easily split from each other. But if the force is coming from the top, the layers are together, so it holds. You don't really have that much issue with that. So that's why some people like to like do it slanted, print slanted. So if a force is coming from here, it doesn't really have much effect. If it's coming from the top, it gets distributed and doesn't really. But you need to consider your use case. If the force is significant enough for you to slant it this way, or it's just minimal, it doesn't do much, so you can still print it this way. So there's a like things you need to consider, which goes back to like the technical stuff. So I hope that helped. And with that, we could end this session finally. Okay.
Okay, Sunday, I thank you for the presentation and the replying to post comments and questions. And what I can say is have a blessed evening from Africa and have a blessed morning or midday from the US side.
Mm.
Okay,
Bye.
next time, bye bye.
You too.